Swayam Prabha. Digital India. Educated India.
So, in the last class, we saw that there was an advantage of choosing a orthogonal set as a basis as opposed to an independent set. Okay. So, what I want to ask is, if I give you an independent set of vectors, okay, is it possible to convert it into a orthonormal set? That is the question, because then see the basis is not uniquely defined. If you take R2, any two independent vectors can be a basis, right. So, you can have millions and zillions of bases, you can take any two independent vectors, because any arbitrary vector can be written as a linear combination. Some of these will be orthogonal, some of these will not be orthogonal. So, if I give you a basis which two vectors, and let us talk in terms of R2, because it is easier for you to understand. Starting with these two vectors, how can I construct two orthogonal vectors which can be formed as a basis, and if I use this as a basis, then it is easy for me to represent any arbitrary vector and get these coefficients, okay, that is the idea. So, we are going to talk about this method called okay. So, in R2, okay, any two independent vectors form a basis, okay, and hence we can have in fact an infinity of bases. That is that this means, okay, what is the meaning of basis? Any arbitrary vector can be written as a linear combo of this basis. That means, if by basis u1 u2, what do I mean by this is a basis? I mean any arbitrary vector v can be written as sigma ci ui. We can talk about R only two dimensional, okay. I can find corresponding C1, C2, now those are the coordinates in that basis, okay. But finding the CIs, for finding the CIs, we have to solve a system of linear equations, okay, that is what we saw. Because what is known is this is known and this is also known, only CIs are unknown. But if we have u1 u2 orthogonal, then finding the CIs is efficient. Of course, if it's 2 equations you can solve, solving 2 equations is efficient, but suppose you have 20 equations, 50 equations, 500 equations when you are doing research, then you can't be solving a system of linear equations 500 by 500, okay. So, is that a better way? So, therefore, it makes sense to have orthogonal set or orthonormal set. So, now, so the question I am asking is, given a u1 and u2 which is linearly independent, can I construct a basis, say E1 E2, which is orthonormal, okay, and E1 E2 will be a linear combination of U1 U2, because I am starting with U1 U2, okay. Okay, this method of getting an orthonormal set from an independent set is called is this Gram-Schmidt orthonormalization. Now consider, again I will just illustrate in 2-dimensional space. This is one vector u1, let me just this is u1 and let us say this is u2. So, u1 u2 they are independent, okay, because they are not collinear. If it is on the same line, then it is dependent. Now, they are not falling on the same line. So, they are definitely independent, and what I want to do is I want to, and they are not perpendicular to each other, they are not orthogonal and their length may not be 1. So, they are not orthonormal, okay. So, this is basically 2 independent vectors are independent. Now, I want to make my objective is to get 2 vectors which have unit length and perpendicular to each other, okay. So, the first vector E1 it has to have unit length, E1 is for unit length, okay, and how do I take U1 and I just divide it by the norm of it, I get a unit length, okay. So, this is basically what you would do, U1 divided by norm of U1 is E1. You already have U1 with you, find the length of it, divide U1 by this vector. So, now this will have unit length, okay, and so now I got one vector which has unit length. I have to now make a second vector which also has unit length and which is perpendicular to this, okay. So, the way I can do it, and I am just going to explain to you geometrically, is I take, so this is U1 and let us say this is E1. So, E1 is also along this line, but it has unit length, okay. I am going to project U2 on U1 or U2 on E1, sorry, I am going to project U2 on E1. What is the meaning of projection? Projection is done to find the angle, remember cos. So, basically for doing the projection I have to take the inner product. So, inner product of U2 on E1 gives the projection of U2 on E1, okay. So, I am going to project it means I am just going to draw this perpendicular. So, this is this thing, let me call it OC, okay. So, OC is the projection of U2 on E1, the magnitude is this and along this line. So, what is OC? OC is basically inner product of u2 on e1 in the direction of e1, okay. So, when I am doing this projection, what am I getting? This is 90 degrees, this is perpendicular. I mean, this you can visualize geometrically. So, what have I done? I have normalized this vector, I get E1. I am finding the projection of U2 on E1, and this projection is along the direction E1. E1 is the unit vector in this direction. So, this vector OC, this vector OC is given by, is in the direction of E1, the magnitude is this projection, okay. Now, you can, this vector I am going to call it G2. What is G2? G2 is this vector, okay, the dot 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 line that I have drawn here. So, U2 will be OC plus G2, okay. So, U2 is OC plus G2. So, what is G2? Is just, is G2 is U2 minus OC, which I already told you is inner product of U2 with E1 times E1, okay. So, but G2 may not have unit norm, may not have unit length. So, what I want to do is I want to make it also of unit length. How do I make this thing of unit length? Divided by the norm of G2, okay. Now, so of course, E1 and E2 have unit norm because I have normalized it, but I have to show that E1 and E2 are perpendicular, okay. How do I show that? So, if I show G2 is perpendicular to E1, then E2 is also perpendicular because in the same direction, okay. How do I show, how to show that G2 is orthogonal to E1? You take the inner product of G2 with E1, if it is 0, it is orthogonal, okay. So, is the inner product of G2 with E1 equal to 0? If it is 0, it is orthogonal. So, I want to calculate the inner product of G2 with E1. G2 already I have defined. So, G2, inner product of G2 with E1 is inner product of U2 minus inner product of U2 with E1 with E1. Remember, this inner product is a scalar, okay, and you had that commutative rule of inner product. So, this is the same as inner product of U2 with E1, this U2 with this minus inner product of U2 with E1 times E1 with E1, okay. This is a scalar. This inner, when you take the inner product, you get some number. So, I should actually do a complex conjugate, but right now let us forget complex conjugate, let us say everything is real. So, now inner product of E1 with E1 is 1 because the norm of E1 squared, right, this is 1. So, then you get this minus that, which is 0. So, basically I explained to you geometrically, how taking the inner product and taking the projection and subtracting gives you a perpendicular vector. That is for you to visualize. But if you do not want to do any geometry, you just want to do it by writing a code to generate the sequence of vectors, this is what you would do. So, they give you two vectors, you just have to use this formula for getting E1 and E2, okay. Now, so supposing you have U1, U2, U3, Now we are, let us say we are talking about R3 space. Okay, this is a basis in R3 and linearly independent. Okay, then how I want to generate E1, E2, E3, three mutually perpendicular vectors. Okay, so E1 will be U1 divided by norm of U1. So that is your first one. What about the second one? Second one will be the same as what we did. I find G2, which is U2 minus inner product of U2 with E1 times E1. So I get my second vector by doing this projection, because it, to me, when I am doing it algebraically, it does not matter if it is 2D or 3D. Okay. For the sake of visualizing geometrically, I talked about R2, but if I am going to use this formula, I am not restricted anywhere that it has to be in R2. Okay. Because this formula, inner product can be for any n dimensional vector. So I can use this to get G2, and again E2 will be same thing, G2 divided by norm of G2. Okay. So what about G3? I need a third vector. To get G3, what would I do? I will take U3 minus, I have to make it perpendicular to both E1 and E2. So I will subtract the projection of E1 and the projection of on E2. Okay. So this is guaranteeing it is G2 is perpendicular to E1. Now to get the third vector, I am taking the third U3 and subtracting from the projection of U3 on E1 and E2. Okay, this is what I am getting. And of course, what is E3? G3 divided by norm of G3. Okay. So now you have to show me, we have to, so let us forget this geometric representation and let us see if G3 is perpendicular to E1 and E2. Okay. We want G3 to be perpendicular to E1 and E2. So what is the inner product of G3 with E1? It is inner product of U3 with E1 minus, this is scalar which is coming out, U3 with E1 E2 times inner product of okay. Basically inner product of this with E1 is the same as inner product of this with E1 minus this with E1 minus this with E1. That is what I have written. Okay. So inner product is projection of this vector is projection of this vector with E1 minus this vector with E1, this vector with E1. We already know E1 and E2 are perpendicular. That is how we constructed it. Okay. And this is 1. So again this will be 0. Similarly, inner product of G3 with E2 will be inner product of U3 with E2 minus inner product of U3 with E1 times E1 with E2 minus inner product of U3 with E2 times E2 with E2. In this case, these two are perpendicular. Okay, so that goes to 0. E2 with E2 is 1. So these two will cancel and I get 0. So basically what I am trying to tell you is that G3 is perpendicular to E1 and E2. I normalize it, I get E3. Okay, so this is the method which you will use. So when you have this algebraic method, you can just use some kind of a formula to get get your basis. Okay. So E1, E2, E3 are, and remember E1, E2, E3 are a linear combination of U1, U2, U3. So basically I give you 3 vectors, you can do some combination, but how to do this combination are arbitrary. There is a very systematic method by which I can get 3 perpendicular vectors. Okay. So now for an n dimensional space, how will I get the I have U1, U2, Un. Okay, I have n independent vectors as the basis. I have n vectors, these are the basis. E1 I am going to generate as U1 divided by norm of U1. And I am going to write Gk as Uk minus sigma k I equals 1 through k minus 1 of what did I do? Yeah, Uk minus E, what is it? EI, thank you. Okay. So that is the general formula which you have. So I am summing over I. So when I have 2, I have only 1 term. When I have 3, I have 1 and 2, 2 terms. 4, I have 3 terms. I am taking more and more projections. Okay. So basically what I have done is I have illustrated for k equals 2, k equals 3, and I am just writing the general formula for k equals arbitrary k or n. Okay. So this you have to do for up till n minus 1, because as many vectors as they are there. This will do for k, and Ek will be Gk divided by norm of Gk. This is for k equals 2 to n. So given a particular linearly independent set, is there only one way you can get an orthonormal set, or you can get multiple orthonormal sets? You can get multiple, because you may choose U1 as the first vector, somebody else may choose somebody else as the first vector. If I give you 10 vectors, you can choose anything as first vector, anything as second vector. So depending on that, you will get different orthonormal sets. Okay, they will all be linear combinations. So basically what I am saying is, we can get multiple orthonormal sets from one set of Ui, because you can decide anything you want as a first vector, anything you want as a second vector, anything you want as a third vector. If I give you 10 vectors, you can choose the last one as the first and then start doing the process. Okay, so there is no uniqueness. Okay. They are all, the only thing is they will all be orthogonal, orthonormal, and that is what you want. But now you have the orthonormal set, you can represent any vector as a linear combination of this orthonormal set, okay, because then you can find this coefficient Ci very elegantly. So, that is the idea. Yeah. Okay. So, what I, rather than start something new, I thought what I will do is I will just kind of summarize whatever we have seen so far, so that you know, you understand the various things now, maybe hopefully in a better way. So, normally you are used to vectors in 2-dimensional spaces, 3-dimensional spaces, where you only have I, j, k, x, y, z coordinates. But what we want to do is we want to come with generalizing things in large dimensional spaces, where the vectors can have, mathematically I like to have the vector can have 10 coordinates, 100 coordinates, because all these equations are coming from some physical system where the number of variables can be very, very large. Okay. So, it is not the vector that I am talking about is not the physical vector you come from in physics, like velocity has 3 components, force has 3 components. So, unknown variables like we saw, you know, in the pipe flow problem, they are my elements of the vectors. Okay. So, mathematically they are my vectors. So, you need to generalize it to higher dimensional space. Okay. So, that is the first thing. So, we are interested in generalizing vectors to higher dimensional space. Here each element could be has a physical meaning, like concentration in the reactor of species I we saw that batch reactor example A, B, C, D, C, A, C, B, C, D were the things, they didn't have anything to do with velocity or force. Okay. And so, basically you have to, we are thinking of vectors as just some variables which have some physical meaning, and so we want to get into abstraction. Okay. And so, then we said we defined this concept of vector space to move to algebraic representation, okay, and get away from the limitations, or rather not limitations, shackles of geometry representation. Geometric representation, I mean what you can physically visualize, right. So, I want to get away from this limitation that I have. So, that is what we are trying to do, and for that we discussed so then we discussed this concept of vector space. In vector space we said has two kinds of things, one is the field, and let us say only real numbers. So, the field of real numbers and vectors closed under scalar multiplication and vector addition. Okay. So, basically when I say a vector space, you take a vector, you multiply it by a real number, you get a vector in the same space. You add two vectors, let us say with n coordinates, I get a vector with n coordinates. So, it is all belonging to the same space. So, Rn is a vector space. Okay. So, Rn a vector with n elements or coordinates belongs to Rn. Okay. Now, after this we spoke about this concept of linear independence. Okay. So, before we spoke about linear independence, we spoke about metric, norms and inner products. Okay. Again, metrics is basically generalized distance. So, just to show that there is more than one way of thinking of distance. Okay. And we saw that you do not have to necessarily think in terms of Euclidean distance, which you are normally thinking. Okay. Similarly, norm is length, generalized length, and inner product is generalized dot product. So, coming back to our question, I think I have the answer to your question. So, is the converse true? So, I said the wrong thing earlier when we were discussing. So, if you think of India, Tamil Nadu and let us say a district, the district is the inner product space. So, if in the district something is defined, it is also defined in Tamil Nadu because it is inside Tamil Nadu, it is inside India. Tamil Nadu is your norm space. Okay. Inner product may not be defined, and the metric is India. So, if you are in the inner product space, you already are in the metric space. So, metric is more general that way because it does not have the constraints of scalar multiplication and vector addition. Okay. So, I think that should make it clear as to why the converse is not true. So, just because you are in Tamil Nadu, you are a Tamilian and also an Indian, but if you are an Indian, but you may not be a Tamilian, that kind of thing. I just had to flip my thinking. Okay. So, now after we decided or discussed all of this, and I said, I mean, concepts of metric, you can use all these other metric definitions because they are maybe more computationally efficient when you are writing computer code to talk in terms of convergence of sequences, for example. Okay. When you are solving iterative methods, using iterative methods to solve nonlinear equations. Now, the other thing we did was talk about linear dependence of a set of vectors ui. So, when I put curly bracket, I mean the set of vectors ui, u1, u2, u3. Okay. So, this is a set of vectors. So, if Ci ui equal to 0 is possible only if Ci equals 0 for all I, then Ui is independent. But even if one Ci is non-zero, okay, then I say it is dependent. And we spoke about, after this concept of thing, we spoke about dimension. Of vector space. This is nothing but the maximum number of linearly independent vectors that you can have in that space, okay. So, we showed that for Rn, the maximum number of linearly independent vectors we can have is n, by choosing an example E1, E2, E3, En, okay. So, in Rn, if we have n plus 1 vectors, they are dependent. Why? Because you have more unknowns, less equations, okay. Knowns, so you can always put the unknowns non-zero, okay. The extra unknowns can be non-zero. I mean, you are free to choose, but and we showed that you can have a maximum of n independent vectors, right, E1, E2, E3, where E1 means only one, the E1 has 1 in the first coordinate, everything else is 0, okay. And we showed by example that there is a maximum of n independent vectors in Rn. What are these vectors? 1, 1, 0, 0. I mean, then have 0, 1, 0, 0, 0, 0, like that. We did this, okay. Third one is 0, 0, 1. Like this you can choose, no. Therefore, that becomes the dimension. So, then we talked about basis. If the dimension of a space is n, then a set of n independent vectors forms a basis, and any vector can be written as a linear combination of this basis. Okay, that is what it means. Any vector can be written as a so V can be written as sigma Ci ui, and what we also found out is, given a particular basis, this representation is unique. For a particular basis, for a particular vector, the Ci's are unique. You can't have more than one solution. Okay, the Ci's are unique. There is only one way by which you can represent in terms of a basis. You can't have different components. So, Ci's can be thought of as components on a particular basis, and there is an advantage of doing things with orthogonal basis. That is what we said, right? Because so if ui is only independent, if ui is independent alone only, then Ci's are found by solving n linear algebraic equations. If ui are orthonormal, we can find Ci's by taking the inner product directly. You don't have to sit and do Gauss-Seidel eliminations, and the problem arises when n is large. Okay, and finally we saw Gram-Schmidt. Orthonormalization to convert an independent set to an orthonormal set. Okay, this is what we have done so far. So, basically whatever I have done is only for 20 minutes. So, now what are we going to do next? You have seen the importance of having these properties you understand, these fundamentals you understand, and now when we go to problems, the idea was to solve different kinds of problems, algebraic equations, ODEs, PDEs. So, we will define something called an operator, and for each problem we will use a basis which is going to be defined by that problem itself. Okay, you will see that when we start doing it, and then there are some properties of orthonormality which come, and so because every time we solve a problem we use the basis generated by that problem itself, we are able to use the same approach for solving algebraic equations, ODEs and PDEs. Okay, so that is the next step. Thank you.